we'll make a start. It's 3 minutes past 2. So welcome back to the Tuesday afternoon session. We've got a great lineup of speakers this afternoon before tea on inference for models. So we've got Theo Kypraios from Nottingham, Alice Corbea from Warwick, TJ McKinley from Exeter, and Phil O'Neill also from Nottingham. So 50% of our contingent are from Nottingham. And so without further ado, I'll welcome Theo to the stage.
Thank you, Chris.
Take it away.
Yeah, thank you. Hello, everyone. Thanks very much to the organizers for having me here. It's a great pleasure. Having said that, I'm a bit worried about whether I'm privileged, about my code, and about the figures in this talk. So hopefully they will pass the standards. So I'm going to talk basically today about the work of two of our PhD students in Nottingham, jointly supervised with me and Phil, George Aristotelus and Jessica Stockdale. So the first part is about data augmentation. Ben talked a little bit this morning about whether or not this problem is solved. It isn't, I'm afraid. And then how to avoid data augmentation. So I only have 40 slides to go through, so hopefully I can do this in the appropriate time frame. So what is the setup? Is the usual kind of setup. We observe some data. We have a model. The model has some parameters. We would like to make inference to infer theta. The observed data likelihood is intractable, and that's actually the main problem. If you are Bayesian, you're going to assign some priors to your parameters. And then if you want to access then the posterior distribution, pi of theta given r, then a solution, not the solution, but a solution is to do some data augmentation. So augment your observed data with the things you wish you had observed, the infection times, and that gives rise to a tractable likelihood. This is just a pictorial representation. So the blue dots are kind of the data that I assume I have. So recovery times of individuals in continuous time. I may want to fit an SIR model, exponential infectious period. And then the red dots are the things that I'm augment my blue dots with, the infection times, and then essentially use MCMC to sample from the parameters and the unobserved infection times given the data. Now, you know, it's a long while ago since we had an algorithm to do this. So back in 1998, 1989. So this is the vanilla, as I call it, MCMC algorithm, where basically what you do is you sample from your target distribution, pi of theta and I given r, by essentially following this very simple algorithm. You initialize your chain, your Markov chain, and then you sample from the model parameters, the full conditional of beta given everything else. The infection rate is beta, gamma is the removal rate. Then you sample from gamma given beta and the infection times in R, and then you sample from the unobserved infection times given the rest. This seems very simple. It is on the face of it, but in reality it is not that easy to make this to work in large populations. So since then, there's been lots of progress in this field by making MCMC to work in lots of different problems, complicated models, kind of large data sets. Many people in this room have contributed. Apologies for not putting all the names on. And why is it challenging? The challenge actually is, I think, it boils down to these three things. So when you try to update the pi of I given r, so the distribution of the infection times given everything else, if you try to update it as a block naively, that is very bad. You know, you will fail miserably. I have failed miserably. It's very difficult to get anything to work. You may want to choose one of individuals and update their infection time, and then update beta, and then update gamma. Or you might do what seems to be working pretty well, is to update the infection times for each individual, but one at a time. So try and make your life a bit easier by choosing, you know, an individual, propose to sample the infection time, given everything else being the same, and carry on doing that. So that seems to work reasonably well. And our PhD student George, you know, has looked into that in great detail. And it seems that if you use a very simple proposal for when you do Metropolis Hastings to update your infection time, is something like this. So if you have a model with an exponential infectious period, you might just propose a candidate infectious period and then get ij from there. If you had something a little bit more exotic, like a gamma distribution or a Weibull distribution, you can do the same. And I'll show you now some graphs that when you do this, things are not too bad. So here is my first graph, and I hope it passes the standards. I only have 3 things. So again, I think I'm within the limits of number 4. So basically, if you look at this picture, focus on the black dots, which basically on the x-axis, I've got the individuals ordered by the time at which they got removed. And the black dots is the acceptance rate in my kind of Metropolis Hastings algorithm I just described. It's an independent sampler, so ideally you want all these black dots to go basically up high to 1. Yeah, that's what you wish, what you hope for, and so on. And you see that it's not sort of not too bad. In this case where we have a small n, so 200, and the R naught was 1.5. The red dots is the inadmissibility kind of proportion, so how often you propose something which is not consistent with your data. And again, most of the time you do well, not so well for the individual who removed last or for the individuals who removed at the early stages, but overall, actually you're not doing that badly. And the green dots are kind of proportion of effective sample sizes. Again, you want green crosses, not dots, to be high up as well. And if you repeat that for other data where R naught now is 2.5, you still have this curvature effect. The mixing is okay, but then as you have an R naught which increases, like here in this case is 5, then things deteriorate. Okay, and then your mixing also actually gets worse. So it's an algorithm that you can apply very easily, and it seems to work reasonably well, but not sort of that great if you want to increase n as well. Now, why this doesn't work very well? So if I just show you here, the dashed line is our proposal that we're using for this particular individual who got removed first, and the black line is the true sort of full conditional. And you see that this is not too bad, okay, when R naught is 2.5 for the individual who removed first. If now I look at the individual who was removed halfway through the epidemic for R naught 2.5, again, the true distribution that I'm sampling from is the black one, the blue is the proposal. Again, I'm not doing actually that badly. But then as I move towards the end to the outbreak, basically I'm proposing from something that's not really nowhere near where I want to sample from. And that's why you see this curvature effect. So in the middle, we are doing pretty well, but at the beginning of the epidemic and at the end particularly, we don't really do that well. And if I now look at a situation where R naught equals 5, that is the sort of distribution I want to sample from, but basically my proposal is kind of like this. So no wonder why this is a bad sampler. So what actually then George did at the time is say, okay, maybe I can be a little bit more clever, and rather than using the same proposal for all the infection times, I'm going to just use a proposal that is dependent on the individual. So rather than proposing from an exponential with rate gamma, maybe propose from an exponential with rate that depends on the individual. Natural question, how do you choose gamma j? We did something very simple, just do some pilot runs to get some idea, and then use from the pilot run some fixed value of gamma j and see how this actually works. George has done a lot of stuff, and in his thesis there are many more simulations than I'm going to show today. But just to sort of show you a few examples, same data as before. Blue, the same thing, the simple kind of proposal. The red is the one I've just described, the individual specific. And you see that it's doing actually a better job. It's closer to the black, but still, when I look at the individual who is removed last, again, I'm not really doing an extremely good job here either. And equally worse, so this was in the, not last, this was in the middle, and this is the last one now for R naught equals 5, again, pretty bad. So, yeah.
Can I ask a really naive question?
Of course.
Right now? So, is this change conditional on the fact that they happen to be the nth person in an epidemic that has a certain shape? Is that condition?
Yeah.
So you're the last guy. You must have had a kind of an
Exactly. So here we condition everything else. Correct. So here all these plots are conditioned on everything else, and basically what I'm saying is it does have an effect as to where you removed in the epidemic. So if you were removed towards the end, then when you look at your full conditional of the IJ, like your infection time, given everything else, it has different shapes.
Even though you programmed it, like this is a simulation.
This is just given some data.
But it looks more like
this is the full conditional. That's the pi of IJ given everything else. So it's not kind of it's not just the infectious period. It's IJ given everything else.
So it's kind of driven by kind of the shape of the epidemic as well.
Conditional on everything else. Yeah. Okay. So again, equally worse in this case. And here's some kind of numbers to show you, which I have extracted from George's thesis, that you have the standard proposal and you've got this individual specific one. And yeah, we do actually kind of a good job, not a massive improvement, but nevertheless, it's a welcome improvement. And it doesn't really take much effort coding-wise, or it's fairly simple to do. Okay, first part of the first part done. For those of you who have worked in this area, you probably now saying, actually, really what I want to do is some sort of block update. Try to update all the infection times at once, but in a clever way. If you do it naively, as I said, this is very bad and we will fail miserably. And apologies for the pronunciation of the name. So Jiang and Pete Neal introduced an algorithm where essentially they suggested, don't be too ambitious. Don't try to update everything, all the infection times as a block, but just use a subset and try to determine this subset by some pilot kind of runs, and use essentially a proposal which is driven by kind of your model. So if you have a gamma infectious period, you might propose from that distribution. Again, this seems to work reasonably well when your block step, the subset of the infection times you propose to update, is small. So this is a population of 500, and we're choosing 15 infection times to update. A and B are some kind of sufficient statistics from the posterior distribution. Just to give you an idea, B is the sum of the infectious period. And so the green dot is where we are, and the blue contours, which you can't see very well, is basically what you are proposing to move from. And basically you are in regions where there's decent probability, decent amount of probability mass. When you increase your sample size, again, green is where you are, then you suddenly propose to update too many of them, and you go really far away from where you want to be. If you try to update even more, then basically, again, no hope for this proposal to work. Okay, so again, so George did a very good job in trying to drill down as to why these things do. This was, I think, well known from experience, but we tried to understand why these algorithms actually do not really work as well. So then this is another picture here. The black dots essentially tell you your acceptance kind of proportion as you increase the block step size. So you can see very early on your acceptance is 0, so you don't really accept anything. And also as you try to update many infection times all at once, you propose things which are not consistent with the outbreak. So you have people who have nobody to have infected them and so on. So you reject a lot. And then George actually came up with this idea where basically we said, let's try and combine what we did before. Let's still do a block update, like a subset, but rather than, again, proposing, using the same value gamma for all individuals, so use essentially individual specific parameters. So in this case, alpha j and gamma j, that's the first part. And the second part is, don't stop there, also try to scale your proposed infection times such that you basically try to do something along the lines of random walk. You don't move too far away from where you are. So you scale your proposed infection times by some kind of parameter ds, which is dependent on which iteration you are, such that we keep the expected value of b kind of the same, which is the sum of the infectious period. So you try basically to hold back and don't really make these jumps, which basically take you to regions with no a large amount of probability mass. So here's an example, the same as before. So green is where we are, blue is the kind of the algorithm of Pete Neal and Jiang, I forgot the first name of the first author, apologies, read this proposal I've just described, and you see that basically we are almost kind of doing a random walk, but in a kind of in a block of step size now 100. So red is where we're proposing, so we don't really have these very large steps and so on. So we will have zero chance of accepting any values here, but where here actually we do much better. Okay. I hope this makes some sense. Sorry. And then if you look at the graph I showed you earlier, so now I can suddenly do much larger blocks. So before, I think up to 15 I was doing okay, but now actually I can increase the block step size, and that actually seems to work very well. Oh no. Okay, some graphs here to show you that this works well, and actually for large populations, large-ish populations, seems to give you, quite a big improvement, especially when you have R naught being equal to 2.5. Right. 2 minutes or 3 minutes and I'm done. I just want to shed some light to this work done by our PhD student Jess. Now, this is change of gears. So rather than doing MCMC, you might hate MCMC and you don't like it, so you may want to do something else. What else can you do? You might say, I'm going to approximate my observed data likelihood with an approximation. Now, you said earlier, Chris, where does the likelihood, where on earth does it come from? It took me about a week when I started my PhD student to understand where on earth this comes from. I think it still takes a long time for people who see it for the first time. It's not obvious how do you actually, integrate the infection times, from this expression. Basically, the idea of our approach, which we term as pair-based likelihood approximations, PBLA, comes from this. So that's probably the most I can get out of me today. So the observed data likelihood can be described by considering all the individuals who ever become infected. Then you have those who avoided infections, those who became infected, those who remain infected for some time and either fail to infect or infect some others. And these events, of course, are all dependent for different individuals. But it turns out that if you consider pairs of these individuals in the population, the likelihood contribution from such pairs is often tractable, or you can approximate it reasonably well. And then if you make the assumption that you have some independence between such pairs, then that can give you an approximate likelihood which you can either kind of maximize or put it through some, MCMC if you like. There's no data augmentation here. Essentially what we are trying to do is we are trying to analytically integrate out the infection times, which is very hard to do, of course, exactly. And there is a bunch of kind of approximations that we have worked on to basically make this feasible. Again, I don't really have time to go through the details, but essentially the same likelihood I showed you here, this guy here, which often you see like in Tom's book and so on, and other places, you can write it down at individual level. This is equivalent as before. And then, you can do some maths and you can, view the likelihood as an expectation. And then there are a bunch of ways to do this expectation, which will give rise to different kinds of approximations. And then you can use those to come up with, an approximate likelihood. I think that's actually all. So you can look more, happy to chat, of course, later on, more in this paper. And here's some figures to convince you that this works. This is from the foot and mouth outbreak. This is what you get from doing this. And this is where you do a long MCMC run. So not kind of, wildly different kind of results. So I think there's merit. Although I spend most of my kind of time in doing MCMC, I think, and data augmentation, I think there is merit in looking at methods which bypass data augmentation. And also answering bench questions in the morning. I don't think this problem is solved. So this is, I think, a contribution to what we've done. But there's a long way to go to do these things in very large population. And people in the room, I hope will agree with me, who are working in large populations, like Chris, for instance. Thank you.
Maybe just some time for a couple of questions. Carl, you posted in the chat. Do you want to voice your questions?
Sure. If you could go back to some of the plots at the very beginning, where you're showing
Some of the
plots at the beginning.
Oh, yeah, sure.
Acceptance rates.
Yep.
So
Maybe just pick one. You mean nothing? Let's say that one. Yeah.
Is the right way to think about the changing proportions over which individual you're talking about here, like an entropy or information stop thinking, because there's more constraint for the middle individuals than there is for the earlier and later ones?
That's a very good question. I mean, we haven't actually done that, but I think this is a long time also since we did this. So I think there's a long way to go by actually looking at those things. So again, we try to find which individuals to update just really by some pilot runs. But I think if one looks into more details as to exactly what you said, I think probably one can get further away. And that's true also for the second part. I didn't, again, have time, as I predicted, to talk about this, but which individuals you block in pairs makes a big difference as to how good your approximation is. So yes is the answer, but I haven't done.
Okay.
Thank you.
Just a little comment.
Yeah.
It's you're doing in your second approach.
Yeah.
It's basically what we call composite likelihood.
Yeah, you can think of it as it's an approximate likelihood. Yeah,
Where the dependence, multivariate dependence is actually
I mean, you give.
Summarized by
Somebody said, oh, you can also think of it as VB. I mean, it's another approximation. It's an expectation of a product. If there's dependence, you take the product. Yeah, you could. Thank you.
Okay, thanks.
Okay, thank you.
We'll move on. So thanks very much, Theo.